planet 124 light-years away, a global ocean world wrapped in a hydrogen sky, and inside its atmosphere, a chemical signature that, on Earth, is only produced by one thing: life. James Webb detected it in April 2025, and it has sparked the most intense scientific war in modern history. While the team that found it stands by their discovery, others are scrambling to find a non-biological explanation. This molecule exists on Earth for one reason only: marine life breathes it out every single day. Now, Webb has found it on an alien world. Tonight, you will discover every clue Webb found out there, and what they reveal changes everything. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. 124 light-years from where you are sitting right now, a planet orbits a dim red star, and for years, no one could agree on what kind of world it actually was. Not because the measurements were uncertain, the data was precise. The problem was stranger than that. Every instrument scientist pointed at this world returned numbers that placed it in territory science had never charted. Too large to be a rocky planet, too small to be a gas giant, sitting in the exact region around its star where liquid water could theoretically exist on a surface, and wrapped in an atmosphere that, when finally examined closely enough, contained something that made researchers stop and read the data twice. This planet has a name: K2-18b. Within a decade of its discovery, it had become the single most studied exoplanet in history. Not because it was the largest, not because it was the closest, but because of what it implied, and because of the question it raised that no planet in all of human observation had ever raised so clearly before. Let's start with how we found it. In 2015, NASA's Kepler Space Telescope was midway through its extended mission, a campaign astronomers called K2, which is where K2-18b gets the first part of its name. The Kepler telescope had a specific, elegant method for finding planets hiding in the dark. Every 30 minutes it stared at a fixed patch of sky and measured the brightness of roughly 150,000 stars simultaneously. 150,000 stars, roughly the number of people who fill the largest football stadium on Earth, every seat occupied, and Kepler was tracking every single one at once. When a planet crosses in front of its star, passing between the star and us, the starlight dims. Barely. Imagine standing a kilometre, about 6/10 of a mile, from a lighthouse on a clear night and watching someone pass a single coin across the lens. The light doesn't vanish. It drops by a fraction of a percent for a few hours, then recovers. Kepler was sensitive enough to catch that. When it caught K2-18b, the telescope recorded a faint repeating dip in the brightness of a small red star in the constellation Leo, one among the hundreds of thousands it watched every night. The dip returned again and again, every 32 days, with clockwork precision. A planet was there, orbiting that star, returning to the same position like a second hand on a clock. The signal was logged, the coordinates were noted, and then astronomers measured what they had actually found. K2-18b has a mass 8.63 times greater than Earth's. Let's make that physical. If you could place Earth on a scale, you would need to stack 8.5 copies of our entire world onto the other side, just to balance K2-18b. Its radius is 2.61 times wider than ours, not taller than our highest mountains, 2.5 times the full diameter of our planet, measured pole to pole. If Earth were the size of a grape, K2-18b would be roughly the size of a billiard ball. But here is where it gets strange. The solar system we grew up learning about has two broad categories for planets: rocky worlds, small, dense, solid beneath your feet, like Earth, Mars, or Venus, and gas giants, enormous spheres of hydrogen and helium with no solid surface to stand on, like Jupiter and Neptune. Every planet ever studied in our solar system or beyond, had slotted comfortably into one of those two families. K2-18b fit neither. Its density, the relationship between how much mass it carries and how much space it takes up, falls precisely in the gap between the two categories. Not slightly off, not just nudging the edge of one family, squarely in the middle, where no clear model existed. Too dense to be a gas giant, not dense enough to be solid rock all the way through. Like a measurement that belongs in neither column of a well-organized table, accurate but homeless. Scientists had a word for planets in this range, sub-Neptunes, but that label described a size, not a structure. It said nothing about what was actually inside, and what was inside K2-18b was the question nobody could answer. That was the first problem. Here is where it gets more complicated. K2-18b orbits its star every 32.94 days, a short year by Earth standards. But Earth's star is not K2-18. The star is a red dwarf, a small, cool, dim star that burns far less brightly than our Sun, so much dimmer that a planet has to orbit much closer to it to receive comparable warmth. K2-18b does exactly that, orbiting in less than a month at a distance that scientists calculated puts it squarely within what astronomers call the habitable zone. The habitable zone is not a guarantee of life. The name has misled many people, and it's worth being precise. The habitable zone is simply the ring around a star where temperatures are neither so hot that liquid water boils away into steam, nor so cold that it freezes permanently into ice. Liquid water is the only condition the habitable zone describes. Mars is technically within our Sun's habitable zone, and its surface holds no liquid water today. Venus skirts the inner edge, and Venus is a furnace with an atmospheric pressure 90 times greater than Earth's. Being in the habitable zone means the temperature is theoretically right. What actually exists on the surface is a separate question entirely. But K2-18b was in the zone, and that single fact changed how urgently scientists wanted to look at it. For 4 years after its discovery, K2-18b was known but largely unexamined. The numbers existed, the coordinates were logged, but looking at the atmosphere of a planet 124 light-years away requires a specific technique and a specific kind of instrument pointed at the right moment. In 2019, a team using the Hubble Space Telescope attempted exactly that. They watched K2-18b transit pass in front of its star over multiple orbits. As the planet crossed the face of the star, a fraction of the starlight didn't travel through empty space. A thin sliver of it filtered through the edges of the planet's atmosphere, and different molecules in an atmosphere absorb different wavelengths of light, each one leaving a distinct chemical fingerprint in the spectrum that reaches our instruments. Think of it like holding a piece of stained glass up to sunlight. The glass doesn't block all the light, but it colors it, selectively absorbing certain wavelengths and letting others through. K2-18b's atmosphere does something similar to starlight, and the pattern it leaves behind can reveal what that atmosphere is made of. What Hubble found in K2-18b's atmosphere was water vapor, the first confirmed detection of water vapor in the atmosphere of any planet in the habitable zone of any star, anywhere. Let's be honest about what that means and what it doesn't. Water vapor in an atmosphere is not an ocean on the surface. Venus carries trace amounts of water vapor in its own sky, and no one is describing Venus as a candidate for life. The Hubble detection didn't prove K2-18b had liquid water below. What it proved was that a molecule chemically associated with liquid water was present in the sky of a world already unusual in almost every other way. That combination, the wrong size, the right zone, water in the atmosphere, was enough to arrest the attention of the entire exoplanet research community. And then came the classification problem, and that is where everything changed. Scientists now had a world on their hands with no satisfying scientific home. It was too large to be rocky, too small to be a gas giant, in the habitable zone, carrying water vapor in its atmosphere, and every attempt to model its interior using existing planetary science produced contradictions. Rocky planet models couldn't explain the density. Gas giant models couldn't explain the size. Hybrid models required interior conditions that had never been observed. The planet was stranded between two worlds of science that had no middle ground. Something had to give. In 2021, a team at the University of Cambridge, led by astrophysicist Niku Madhusudan, published a paper proposing that K2-18b was not just an unclassified oddity. It was the prototype for an entirely new class of planet, one that had never been formally described, one that the universe apparently makes in large numbers, and one that planetary science had simply never thought to look for. They named these worlds Hycean planets, from hydrogen and ocean. The concept works like this. A Hycean world has a thick atmosphere rich in hydrogen and helium, not the thin oxygen-nitrogen blend we breathe on Earth, but a deep, heavy blanket of the two lightest elements in the universe. And beneath that atmosphere, instead of rock, instead of gas, lies a surface of liquid water, a global ocean with no continents, no coastlines, no land, just water, unbroken in every direction across the entire planet, meeting the atmosphere at the horizon no matter where you look. Picture Earth's Pacific Ocean, the largest continuous body of water on our planet, stretching over 12,000 miles, about 19,000 kilometers, from one side to the other. The Pacific alone covers more surface area than all the dry land on Earth combined. It is, by the scale of human experience, almost incomprehensibly large. A Hycean ocean would make the Pacific look like a small pond in a back garden. An ocean that is not a feature of the planet, an ocean that is the planet. Now consider what might live in it. On Earth, life doesn't only exist at the sunlit surface. In the deepest trenches of our own oceans, far below where any sunlight penetrates, under pressures that would crush a submarine, in total and permanent darkness, ecosystems thrive around hydrothermal vents on the ocean floor. Bacteria, tube worms, shrimp, crabs, entire food chains, sustained not by sunlight, but by the chemical energy rising from the seafloor itself. Life, it turns out, doesn't need the sun. Life needs chemistry. And a global ocean sitting above a rocky seafloor, receiving the planet's internal heat from below, potentially carries that chemistry in abundance. The Cambridge team argued that a Hycean ocean could provide habitable conditions on a scale vastly larger than Earth's oceans allow. Not guaranteed, not proven, but physically plausible in the way that Earth's deep sea vents are physically plausible, and we know what lives there. This wasn't a proposal that K2-18b hosted life. It was something quieter and more important than that. It was a demonstration that the range of conditions in which life could theoretically survive was dramatically wider than planetary science had previously considered, and K2-18b, this billiard ball of a world orbiting a dim red star in Leo, was the best candidate example of that wider range that science had ever found. Scientists from Cambridge to NASA to universities across Europe and Asia began targeting K2-18b with every available instrument. Not as one interesting target among thousands, as the target. The one world above all others that most urgently demanded to be understood. And then the James Webb Space Telescope, built over 2 decades, launched on Christmas Day 2021, carrying the most sensitive infrared detectors ever constructed, turned its 18 gold-coated mirrors toward that dim red star. What those mirrors found is the reason this story is being told. But before we get to what Webb detected, sit with this for a moment. The light we use to read K2-18b's atmosphere, the light that filters through its sky and travels across the void toward our instruments, left that planet 124 years ago. It has been traveling since the early 1900s, since before any human being had left the ground in a powered aircraft. The Wright brothers would not make that 12-second flight at Kitty Hawk until 1903, and that light was already 2 years into its journey, since before the first radio broadcast, since before the word exoplanet existed in any language. That light was already on its way, and the instruments capable of reading it had not yet been imagined, let alone built. The question scientists carried into the Webb era was not simply whether K2-18b had the conditions for life. The question was, what kind of world this actually was, what its atmosphere was truly made of, what those molecules implied, and what a world with no land and a sky of hydrogen actually looks like from the inside out. Because K2-18b, the planet that forced science to invent a new category, turns out to be stranger in its details than even the new category fully captures, and understanding why requires understanding what this world actually is, not just what we call it. What we call it is a Hycean world. What it is something we have never encountered before. A Hycean world. The word sounds almost invented, and in a way it was, specifically to describe K2-18b. But having a name for something doesn't mean we understand it. And the more carefully scientists examine this planet, the more its details resist every framework we've built for how a world should work. Let's think about what K2-18b actually is, not what category we've assigned it, not the label, the place itself. Here is the challenge. Nobody has visited K2-18b. No probe has flown through its atmosphere. No lander has touched its surface, if it even has one. Everything we know about this world has been assembled from light, starlight that filtered through the outermost edges of its atmosphere as the planet passed in front of its star, a thin sliver of photons carrying a chemical fingerprint, travelling 124 light-years to fall on a mirror in space. From that, scientists have attempted to reconstruct an entire world. What they have assembled is unlike anything in our catalogue. The broad picture of a Hycean planet, the category K2-18b inspired, has a specific, unusual structure. Below a deep hydrogen-helium atmosphere sits not rock, not ice, but liquid water, a global ocean. Not an ocean in the way Earth has oceans, bodies of water surrounded and interrupted by land. An ocean that is the entire surface of the planet, extending in every direction, unbroken, from pole to pole. Below that ocean, models suggest the pressure builds so quickly and so intensely that water eventually stops being water in any form we'd recognize, compressing into exotic high-pressure phases, denser than normal ice, that exist nowhere in nature at the scales familiar to us. That is the model, the broad outline. But the details of this world are stranger and more specific than any outline can capture. Let's talk about the star first, because the star controls almost everything. K2-18 is a red dwarf. That means it is small, cool, and radiates light that is almost entirely in the red and near-infrared part of the spectrum. Wavelengths far redder, far longer than the yellow-white light our own sun produces. Imagine the light of a deep autumn sunset. Not the moment just before the sun disappears, but an hour after, when the sky has turned copper and amber and the light on everything around you is warm, thick, almost orange. That is the kind of light K2-18 produces, not as a brief atmospheric moment, but as its constant, permanent output. Every moment of every day on K2-18b would be lit the way the edge of dusk is lit here on Earth. But here is the first deep strangeness of this world. K2-18b almost certainly does not have a day, not in the way we experience one. When a planet orbits very close to its star, as K2-18b does, completing its year in just under 33 days, the gravitational pull of the star slowly synchronizes the planet's rotation with its orbit. The same mechanism that keeps the same face of our moon always facing Earth operates here at planetary scale. The scientific term for this is tidal locking. One hemisphere of K2-18b almost certainly faces its star permanently, bathed in that deep amber light, without pause, without respite, for billions of years. The other hemisphere faces permanent darkness, permanent cold, permanent night that has never once in the planet's entire history been broken by a sunrise. No rotation, no dawn, no dusk. Just two halves of a world, one always burning, one always frozen, locked in place forever. The burning hemisphere would receive constant radiation from a star it can never turn away from. The dark hemisphere would be exposed to the unfiltered cold of space indefinitely. Both extremes on their own would likely be hostile to any life resembling what we know. But there is a third region. Between the permanent day side and the permanent night side, running like a belt around the entire planet, lies a boundary. Scientists call it the terminator zone, the region where the two hemispheres meet. A narrow strip of perpetual twilight where the star hangs permanently low on the horizon, where temperatures are neither scorching nor frozen but somewhere in between, where the chemistry of the atmosphere may reach a kind of equilibrium unavailable anywhere else on the planet. On Earth, the most habitable latitudes are not the equator, baking in constant direct sunlight, and not the poles, locked in freezing darkness for months at a time. Life is most diverse and most abundant in the temperate bands in between. The terminator zone of a tidally locked world may function the same way, cosmically scaled. A permanent ribbon of survivable conditions wrapping the entire planet. Some models suggest this zone could reach temperatures somewhere in a range consistent with liquid water at the surface. Not guaranteed, not proven, but physically plausible. And physically plausible, when we are talking about a world with a global ocean, is worth taking seriously. But what does the sky of this region look like? In the terminator zone, the star would be fixed near the horizon, always there, never rising, never setting. The sky above would depend on how the atmosphere scatters that deep red light. A hydrogen-rich atmosphere scatters shorter wavelengths differently than the nitrogen-oxygen sky we know, and the light coming in is already shifted toward the red and infrared end of the spectrum. The result, according to models, would be a sky of amber and copper, streaked with violet and deep burgundy. Not a sky that cycles through colours as ours does with the turning of the day. A fixed sky, a permanent palette of colours that never change, never shift, hanging over an ocean that stretches in every direction to the horizon. There are no seasons on this world, no mornings, no evenings. The sky looks the same today as it did 10 million years ago. It is profoundly alien. And yet the question scientists keep circling back to is this: could something live there? Let's consider the ocean itself, because this is where the science becomes genuinely astonishing. If K2-18b is a Hycean world, its ocean is not like ours in almost any respect beyond the basic chemistry. Earth's oceans have an average depth of about 3.7 kilometers, roughly 2.3 miles. The deepest point, the Mariana Trench, reaches just under 11 kilometers, about 6.8 miles. At that depth, the pressure is roughly 1,000 times greater than at the surface. Extreme, but survivable for life. We know because life has been found there. K2-18b's ocean, based on the planet's mass and the physical models scientists have run, would be vastly deeper, possibly tens or hundreds of kilometers deep. The numbers are difficult to pin down without direct observation, but the consensus is that this ocean has far more water than anything in our solar system, and it sits above an interior that generates substantial pressure simply from the weight of everything above it. Here is the strange part. At depths far below any surface, under pressures that have no comparison in human experience, water stops being liquid. But it does not become steam. Under extreme pressure, water can compress into solid phases that are denser than normal ice, and can exist at temperatures that would melt ordinary ice almost instantly. Scientists call these exotic high-pressure water phases structures like Ice 7, which forms when water molecules are squeezed so tightly They lock into a crystalline arrangement, yet remain at temperatures far above freezing as we know it. Ice that exists not because it's cold, but because it's crushed. Below the liquid ocean on K2-18b, models suggest this kind of exotic compressed water may form a thick inner layer. Not rock, not the kind of hard seafloor we imagine when we picture a world's interior. A floor made of a state of matter that only exists under conditions we can barely produce in a laboratory. No rocky bottom, no hydrothermal vents drawing heat from a volcanic interior, the way Earth's deep ocean vents do, or so scientists initially assumed. And here is where the science takes a turn that changes the framing entirely. For a long time, the instinct when imagining extreme deep ocean pressure was to think of it as destructive. The pressures at the bottom of K2-18b's ocean would be enormous, far beyond anything at the bottom of the Mariana Trench. Surely, in that environment, complex molecules would be crushed, chemistry would be suppressed, life would be impossible. But some researchers have challenged this assumption directly. Pressure doesn't only destroy. In the right conditions, extreme pressure can stabilize. It can force molecules into configurations that don't exist at lower pressure. Configurations that are, actually, more chemically reactive, more capable of complex bonding, more conducive to the kinds of molecular interactions that, on Earth, we associate with biological chemistry. The same compression that produces exotic water phases may also create conditions where certain organic molecules become more stable, not less, where certain reactions happen faster, where certain chemical structures persist long enough to matter. On Earth, right now, life thrives in an environment that looks completely hostile on the surface. The hydrothermal vent systems of our own deep ocean floor, cracks in the seafloor where heat from the planet's interior escapes into the water, support entire ecosystems. Tube worms that grow over 2 meters long, about 6 feet, in water that contains no sunlight and no oxygen in the way surface life needs it. Bacteria that derive energy entirely from the chemical reactions between hot, mineral-rich water and cold ocean water. Shrimp whose eyes have adapted not for visible light, but for the faint infrared glow of the vents themselves. None of this life uses the sun. All of it uses chemistry. The question K2-18b forces science to confront is not whether life needs a surface, sunlight, or breathable air. Those requirements come from studying one planet, for one kind of life, around one kind of star. K2-18b asks what life actually requires at its most fundamental level, and the answer from Earth's own deep-sea ecosystems is simpler and more general than we assumed. Chemistry, energy, time. K2-18b may offer all three in extraordinary abundance. Let's put this in perspective because the numbers here are staggering in a specific way. Earth's total ocean volume, all of it, every drop from the surface to the deepest trench, amounts to roughly 1.3 billion cubic kilometers, about 312 million cubic miles, an almost incomprehensible amount of water. But K2-18b is 2.6 times the radius of Earth. Volume scales with the cube of the radius, meaning a planet roughly 2.5 times wider contains not 2.5 times as much interior space, but closer to 17 times as much. Even accounting for the fact that not all of that volume is ocean, a Hycean world the size of K2-18b could plausibly hold an ocean with hundreds of times more water than all of Earth's oceans combined. Hundreds of times more volume. Potentially, if the Hycean model is correct. That is not just a bigger version of what we have. That is a different scale of environment entirely. A world where the habitable domain, the space in which life could theoretically exist, is not a thin film clinging to the surface of a rocky planet, but an enormous three-dimensional volume extending from the temperate terminator zone all the way down through a deep, pressurized, chemically complex ocean. And yet, This is where the scientific debate matters, and it is a genuine debate, not a settled question. Not every scientist accepts the Heysian interpretation of K218b. A competing model exists, documented, published, peer-reviewed, and it reaches a starkly different conclusion. Some researchers argue that K218b is not a Heysian world at all. Their models suggest it may be a gas-rich sub-Neptune, a planet with an extended hydrogen atmosphere that thickens as you descend, growing denser and hotter without ever presenting a clean liquid ocean surface, more like a small version of Neptune than a water world. In this model, there is no habitable ocean, no temperate zone above a liquid surface, just a deepening, crushing gradient of gas that eventually becomes something else, at pressures too extreme for any chemistry we associate with life. The two models, Heysian ocean world versus gas-rich sub-Neptune, produce very similar atmospheric signatures when viewed from outside. Both have hydrogen-dominated atmospheres. Both absorb and emit light in broadly similar ways. From a distance of 124 light-years, they can be difficult to distinguish. The difference is everything. On one side of this debate sits a world with the largest potentially habitable environment we have ever identified. On the other side sits a world with no habitable surface at all, just a hostile, uninhabitable gradient from atmosphere to crushing interior. And here is the uncomfortable truth. The measurements taken so far cannot conclusively distinguish between the two. The interior of K218b remains, as of today, the most important unanswered question in exoplanet science. We cannot drill into it. We cannot send a probe. We cannot measure the density with enough precision to separate the models unambiguously. The only window we have into this planet is its atmosphere, the outermost edge, the thin chemical fingerprint it leaves in starlight, which means the atmosphere is everything. What the atmosphere contains, what molecules it holds, what those molecules imply about the conditions below. Because here is what the two competing models agree on, completely. If K218b is a Heysian world, a living ocean beneath a hydrogen sky, its atmosphere should carry chemical traces of what lives in that ocean. Chemistry doesn't stay contained at a surface. It rises. It mixes. Biological processes leave molecular signatures in the air above them. On Earth, the gases that fill our atmosphere are not geologically neutral. They are products of life, oxygen from photosynthesis, methane from microbial digestion, compounds produced by marine organisms and carried upward by wind and evaporation. Strip life from Earth and the atmosphere would change chemistry over geological timescales. The two are connected. If a living ocean exists beneath K218b's sky, something of it should appear in the molecules above. And if K218b is a lifeless sub-Neptune, then the atmosphere should look like what physics and chemistry alone would produce. Predictable, explainable without biology, clean in the way that a place without life is chemically clean. The James Webb Space Telescope, trained on K218b for hundreds of hours across multiple observing runs, studied that atmosphere in extraordinary detail. What it found was not clean. What it found was not easily explained. And one of the molecules it detected, faint, contested, but real enough to demand an answer, has only ever been produced in any quantity measurable by any instrument we have ever built in one way. By life. 2 words. And they deserve to sit there for a moment before we go any further, because what came before them, the data, the instruments, the years of careful observation, was not hyperbole. It was chemistry, specific, measurable, documented chemistry, the kind that does not appear in a dead sky. Let's talk about what the James Webb Space Telescope actually found in the atmosphere of K218b. Not the headline, the science underneath it. To understand what Webb detected, we need to understand precisely what it was doing when it looked at K218b. Webb carries an instrument called NIRSpec, the Near Infrared Spectrograph, A spectrograph is an instrument that splits light apart by wavelength, the way a prism splits white light into a rainbow and records exactly how much light arrives at each wavelength. The near-infrared part means it is sensitive to light, just beyond what the human eye can see, a range of the electromagnetic spectrum that is invisible to us, but rich with molecular information. When K2-18b passes in front of its star, a thin ring of starlight filters through the outermost edges of the planet's atmosphere on its way to Webb's mirror. Each type of molecule in that atmosphere absorbs specific wavelengths of that light. Not all wavelengths, not random ones, but precise and repeatable ones, like a chemical signature that is unique to each molecule. Methane absorbs at one set of wavelengths, carbon dioxide at another, ammonia at another still. Every molecule leaves a fingerprint in the light that reaches the telescope, and a NIRSpec reads those fingerprints with extraordinary precision. Think of it like this. Imagine a particular perfume, distinct, specific, unmistakable. If you walk into a room and that scent is present in the air, you don't need to see the bottle to know it was there. NIRSpec detects the scent of molecules in an atmosphere 124 light-years away, not by smell, but by the wavelengths of light they absorb. The principle is the same. The fingerprint is just as real. In 2023, using this instrument across multiple observations of K2-18b, the Cambridge team led by Niku Madhusudan published a result that immediately commanded the attention of the entire scientific community. Webb's NIRSpec detected methane and carbon dioxide in K2-18b's atmosphere. Let's be precise about what that means, because the significance can slip by if we're not careful. Methane, a molecule made of one carbon atom bonded to 4 hydrogen atoms, had been detected before in various planetary atmospheres across the solar system. Carbon dioxide, one carbon atom bonded to 2 oxygen atoms. Similarly, neither molecule is extraordinary on its own, but these were the first detections of carbon-bearing molecules in the atmosphere of any planet, orbiting within the habitable zone of any star, anywhere. Not just the first for K2-18b, the first ever. In all of human astronomical history, no instrument had confirmed carbon chemistry in an atmosphere where liquid water could theoretically exist on a surface. That alone stopped scientists. But then the chemistry became strange. In a hydrogen-rich atmosphere, the kind K2-18b likely has, methane and carbon dioxide should not comfortably coexist in the proportions Webb measured. When carbon, hydrogen and oxygen are available in a hydrogen-dominated environment, chemistry tends to drive toward a different equilibrium. Under the right conditions, those elements should also produce carbon monoxide, a molecule of 1 carbon and 1 oxygen atom, and in a lifeless world, carbon monoxide should accumulate at detectable levels. The chemistry demands it. Webb found no carbon monoxide, not trace amounts, below the threshold of detection. The combination of methane present, carbon dioxide present, and carbon monoxide absent in a hydrogen-rich atmosphere is, according to the models, chemically difficult to explain without invoking something that actively processes carbon, something that takes in certain molecules and produces others, something that disrupts what dead chemistry would otherwise produce. That was the first signal. But the absence of something else deepened the mystery further. In a lifeless, hydrogen-rich atmosphere, a world where chemistry runs on physics alone, with no biological interference, nitrogen and hydrogen readily combine to form ammonia. Ammonia is not an exotic compound. It is one of the simplest and most stable nitrogen-hydrogen molecules in chemistry. In a lifeless sub-Neptune, or a Hycean world with no ocean biology, ammonia should accumulate steadily in the upper atmosphere and remain detectable for billions of years. The models are clear on this. Webb found ammonia at levels far below what a lifeless world of this type should carry, below what dead chemistry predicts, below what every model of a biologically inert hydrogen-rich atmosphere produces. Something was depleting it, or preventing it from accumulating in the first place. On Earth, ammonia is rapidly consumed by biological processes. Microorganisms incorporate nitrogen from ammonia into organic compounds, the building blocks of proteins, DNA, cell membranes. Life eats ammonia. That is why Earth's atmosphere is not saturated with it, even though the chemistry that produces ammonia operates continuously in our environment. The absence of ammonia in K218b's atmosphere does not prove biology, but it is exactly what biology would predict. A living ocean, consuming nitrogen compounds from above, would leave this specific gap, this precise deficit in the atmospheric chemistry. Methane present, carbon dioxide present, carbon monoxide absent, ammonia depleted. Each piece on its own could be explained. Together they pointed in one direction, and then the team looked more carefully at a signal they had noticed, but initially declined to announce. In the 2023 NIRSpec data, buried beneath the cleaner signals of methane and carbon dioxide, something else appeared. Faint, uncertain. Scientifically described at roughly 2 sigma significance, meaning the signal was real enough to notice but not strong enough to publish as a confirmed detection. In science, 2 sigma means the signal has about a 1 in 20 chance of being random noise. Interesting, worth watching, not enough to build a claim on. The molecule was dimethyl sulfide. Before we go any further, let's be exact about what dimethyl sulfide is and why its presence, even as a whisper, stopped the Cambridge team in its tracks. Dimethyl sulfide is a sulfur-containing organic compound. On Earth, the main source of dimethyl sulfide in the atmosphere is marine life, specifically phytoplankton and other microbial organisms living in the ocean. When these organisms metabolize a compound called dimethyl sulfonopropionate, produced naturally in their cells, they release dimethyl sulfide as a byproduct. The compound rises from the ocean surface into the air. And if you have ever stood at a beach and noticed that particular sharp, clean, briny scent that signals you are near the sea, the smell of the ocean itself, a significant portion of that smell comes from dimethyl sulfide. It is, literally, the chemical breath of living marine ecosystems. No volcanic reaction produces dimethyl sulfide at detectable atmospheric concentrations. No lightning discharge. No known geological process. Scientists have spent decades looking for an abiotic pathway, a non-biological chemistry, that could produce dimethyl sulfide at the levels we measure in Earth's atmosphere, and none has been found that works at scale. On Earth, dimethyl sulfide is effectively a biosignature, a chemical flag that says, "Living things processed this." That molecule was appearing in K218b's atmosphere, faintly in 2023. But it was there. The Cambridge team did not publish on that hint. They went back. This time with a different instrument. Webb carries a second spectrograph called MIRI, the mid-infrared instrument. It operates in a different part of the infrared spectrum from NIRSpec, detecting longer wavelengths where different molecular signatures are visible. Crucially, MIRI can independently cross-check signals seen in NIRSpec data. Same sky, different wavelengths, a second chemical witness. They observed K218b across multiple transits with MIRI. Not one observation, multiple. Each time the planet crossed its star, they gathered more data. The signal-to-noise accumulated. In April 2025, the Cambridge team published the result. The signal had not gone away. The dimethyl sulfide detection reached 3 sigma, 3 standard deviations above the background noise. What had been a faint whisper in 2023 was now a statistically meaningful signal. 3 sigma means a probability of approximately 0.3%, less than 1 in 300, that the signal appeared by random chance. And they had found something else alongside it, a closely related molecule, dimethyl disulfide, same chemical family as dimethyl sulfide, same biological origins on Earth, also produced primarily by marine microbial life, also lacking any known abiotic pathway that would produce it at detectable atmospheric concentrations. 2 molecules, same family, Same biological origin on Earth, both present, both confirmed across multiple instruments, both at levels inconsistent with known non-biological chemistry. Not slightly strange, profoundly strange. Let's step back and look at the full picture, because individually, each of these findings can be argued. Together, they form something harder to dismiss. Carbon dioxide, present in proportions consistent with a carbon processing environment. Methane, present in amounts the models struggle to explain without active chemistry. Carbon monoxide, absent when dead chemistry says it should be there. Ammonia, depleted when lifeless atmosphere models say it should accumulate. And now, dimethyl sulfide and dimethyl disulfide, present at a 3 sigma confidence level through 2 independent instruments across multiple observations in a molecule family that, on the only planet we have ever studied in any detail, has one overwhelmingly dominant source, a living ocean. The scientific term for what these molecules represent when considered together is a biosignature ensemble, a collection of chemical signals that, as a group, point toward biological activity more strongly than any single signal could on its own. On Earth, no single atmospheric gas proves life exists, but the combination of oxygen, methane, and nitrous oxide in our atmosphere, in the ratios we observe, would be immediately recognized by any sufficiently advanced alien spectrograph as the product of a biosphere. The combination breaks what dead chemistry would predict. The combination found in K2-18b's atmosphere breaks what dead chemistry predicts. That is the honest summary. Not a single smoking gun. A coherent chemical argument, built from multiple independent observations, pointing with quiet but insistent persistence toward the same conclusion. Something in that sky, or in the ocean beneath it, may be alive. But here is what makes this story genuinely difficult and genuinely important. The 3 sigma threshold is meaningful. It is not nothing. In most scientific fields, a 3 sigma result would warrant serious attention, further investigation, and cautious but real excitement. But 3 sigma is not the end of the road. The gold standard in physics, the threshold at which a result is formally declared a discovery, sits at 5 sigma, a probability of roughly 1 in 3.5 million that the signal is noise. K2-18b's dimethyl sulfide signal has not crossed that threshold, and the scientific community has not stayed quiet. Other researchers working with the same data have reached different conclusions. A NASA-led team analysed the same JWST observations and found the evidence for dimethyl sulfide less conclusive than the Cambridge team's interpretation. A separate study identified what it described as contamination in the mid-infrared data, a form of systematic noise that could, in principle, mimic a molecular signal. The debate is real, the data is contested, the question is alive, and this is not a weakness in the story of K2-18b. This is exactly how science should work, openly, rigorously, with competing teams checking each other's conclusions against the same evidence. The strongest scientific results are the ones that survive the harshest scrutiny. What has not been disputed is this: the molecules are there. The chemical picture is unusual. The combination of signals points somewhere that standard lifeless chemistry does not easily reach. What remains unresolved, urgently, critically unresolved, is the instrument that made these detections possible. What exactly did Webb see? How did it see it? And what does it mean that a machine built by human hands, floating 1.5 million kilometers, about 930,000 miles, from the planet that built it, is now capable of reading the chemistry of an ocean world over 100 light-years away? To understand what this detection actually means, and why, the scientific debate about it matters so deeply. We need to understand the instrument at the center of it. We need to understand what Webb is, how it works, and what it took to build something that could hear a signal this faint, from this far, in the cold, dark silence between the stars. And understanding Webb is not a detour from the story of K2-18b. Webb is the story. Without it, those molecules remain unread. That chemical argument remains silent. The signal that has set the scientific community debating, that has forced astronomers to confront a question they have been building toward for decades, travels all the way from a world 124 light-years away and arrives here at an instrument built by human hands that almost wasn't built at all. Let's talk about what Webb actually is, because the scale of what it does and the precision it requires is itself something that borders on the extraordinary. On December 25, 2021, an Ariane 5 rocket lifted off from the Guiana Space Center in Kourou, French Guiana, a launch facility positioned deliberately close to the equator, where the rotation of the Earth gives rockets an extra boost as they climb. The payload was the James Webb Space Telescope, folded like a piece of origami into a shape narrow enough to fit inside the rocket's fairing. After 25 years of engineering, 2 billion hours of combined human work across 14 countries, and a budget that eventually reached approximately $10 billion. The launch window had been tight, the orbit Webb was heading to was unusual, and the telescope itself, once deployed, could never be repaired. Not because it was too far away, though it would be, but because the place it was going was too cold, too dark, and too precisely calibrated to ever survive a human touch again. Webb was aimed at a point in space called the Sun-Earth L2 Lagrange point. A Lagrange point is a location in space where the gravitational pull of two large bodies, in this case the Sun and the Earth, balances with the orbital motion of a smaller object, in such a way that the smaller object stays in a fixed position relative to both. Think of it like a small boat sitting in a river at exactly the point where the current from one direction and a steady opposing wind exactly cancel each other out. The boat stays still without any engine. L2 is that kind of naturally stable pocket in space, roughly 1.5 million kilometers, about 930,000 miles, directly behind the Earth as viewed from the Sun. 1.5 million kilometers. The Moon sits about 384,000 kilometers, approximately 239,000 miles from Earth. So Webb is positioned nearly 4 times further from us than the Moon, in the direction of deep space, hovering at a point where the competing gravitational forces of the Sun and Earth hold it in a quiet equilibrium. No astronaut has ever been there. No spacecraft before Webb needed to be so cold, so still, so far. Here is the central engineering problem Webb was built to solve, and it requires understanding what infrared light actually is. Human eyes are sensitive to a narrow band of the electromagnetic spectrum, what we call visible light, the wavelengths that bounce off objects around us and let us see color, shape, and motion. Infrared light sits just beyond the red edge of what we can see. We cannot see it with our eyes, but we feel it constantly. The warmth you sense when you hold your hand near a radiator without touching it, that is infrared radiation. The heat your own body radiates into a cold room, that is infrared. Every object that has any warmth at all radiates infrared light in proportion to its temperature. This is the problem. The molecules in K2-18b's atmosphere leave their chemical fingerprints most clearly in the infrared part of the spectrum. To read those fingerprints, Webb needed mirrors sensitive enough to detect extraordinarily faint infrared signals from across 124 light-years. But a mirror at room temperature radiates its own infrared heat, like trying to hear a whisper while standing next to a jet engine. The mirror's own warmth would drown out everything Webb was trying to hear. The solution was to make the mirror cold. Not just cool, profoundly, precisely cold. Webb's primary mirror operates at below -233 degrees Celsius, 50 degrees above absolute zero, the theoretical point at which all molecular motion stops. To give that number a physical reference, the surface of Pluto, the outermost known dwarf planet in our solar system, sits at roughly minus 230 degrees Celsius. Webb's mirror is colder than the surface of Pluto. It sits in perpetual darkness, shielded from the Sun, the Earth and the Moon by a 5-layer sunshield the size of a tennis court. Each layer thinner than a human fingernail, each one cooler than the last, reducing the heat reaching the mirror from the equivalent of a bonfire to the equivalent of a single candle flame, and then to less than that. At that temperature, the mirror radiates almost no infrared heat of its own. The noise floor drops low enough that signals from the edges of the observable universe become readable, and signals from K2-18b become, in principle, readable too. Webb's primary mirror spans 6.5 meters across, just over 21 feet. A mirror that size cannot be launched in one piece. No rocket fairing in existence is wide enough. So the mirror was engineered in 18 separate hexagonal segments, each one coated in gold, chosen not for elegance but for physics. Gold reflects infrared light with exceptional efficiency, losing less signal than silver, aluminum, or any other reflective surface commonly available. Each segment is made of beryllium, a metal chosen for being both extraordinarily lightweight and dimensionally stable at cryogenic temperatures, meaning it does not warp or shift as it cools. 18 hexagons, each one the size of a dining table, each one polished to a surface accuracy measured in nanometers, billionths of a meter. To understand what that means, a human hair is roughly 80,000 nanometers wide. The mirror segments are smoothed to within a few nanometers. If you scaled Webb's mirror up to the size of the continental United States, the largest imperfection on its surface would be roughly the height of a human thumb. These segments fold down for launch, then unfold and align themselves in space with mechanical precision that took years to verify on the ground and days to execute in orbit. A single misaligned segment would compromise the entire telescope. All 18 aligned perfectly, and then the telescope turned toward the sky. Here is the true scale of what Webb was being asked to do when it turned toward K2-18b. The planet does not glow. Webb does not take a photograph of it in the way we might photograph the moon or a galaxy. K2-18b is dark, small relative to its star, and lost in the glare of a star 124 light-years away. What Webb measures is the light of the star, and the changes in that starlight caused by the planet's passage. The technique is called transmission spectroscopy. As K2-18b crosses the face of its star, a thin ring of starlight, just the light that grazes the very outermost edge of the planet's atmosphere, passes through that atmosphere on its way to Webb's mirror. Different molecules absorb different infrared wavelengths of that light as it passes through. Methane absorbs here, carbon dioxide absorbs there, dimethyl sulfide absorbs at a precise set of wavelengths specific to its molecular structure. What arrives at Webb after passing through K2-18b's atmosphere is starlight, with specific wavelengths subtly dimmed, each dimming a chemical fingerprint of what the light passed through. Now consider the scale of the challenge. K2-18b's atmosphere represents a thin shell at the edge of a planet that is itself tiny compared to its star. The fraction of total starlight that actually passes through that atmosphere during a transit is vanishingly small, and the fraction of that already tiny sample that gets absorbed by any one specific molecule is smaller still. The signal Webb is hunting, the dimming of specific infrared wavelengths caused by dimethyl sulfide in K2-18b's atmosphere, amounts to roughly 1 part in 10 million of the total starlight arriving at the telescope. 1 part in 10 million. Picture a concert hall with 10 million people inside. One person in that hall whispers a single word. Webb's task is to hear it. To achieve this, nothing can go wrong. The telescope must point at the same star for hours at a time without drifting. The detectors must remain perfectly calibrated. The sunshield must hold the temperature of the mirror constant. The electronics must introduce no additional noise into the signal. The software processing the data must distinguish between genuine molecular absorption and instrumental artifacts. false signals produced by the telescope itself. Webb observes each transit of K2-18b multiple times, repeated passes. The signal builds with each observation. The noise, being random, averages out over multiple runs. The true molecular signatures, being consistent, accumulate. The data then goes to multiple independent analysis teams. Each team uses different mathematical methods, different software pipelines, different assumptions. If a signal survives all of those independent cross-checks, if it appears consistently regardless of who is looking and how they are processing the numbers, it is real. The process takes months, not days. Months of calibration, analysis, argument, and verification before a result reaches publication. That is why the 2023 detection took months to publish after the observations were completed. That is why the 2025 MIRI results required a separate instrument, separate observation runs, and a separate analysis before the Cambridge team was willing to put their names on a paper claiming 3 sigma confidence in dimethyl sulfide. They were not being slow, they were being rigorous, and rigor, in this case, is the only thing that makes the result mean anything at all. Imagine standing in a field on a moonless night, 124 light-years away, a distance so vast that if you travelled at the speed of a commercial aircraft, the journey would take over 1.5 billion years. A planet is crossing in front of its star. The light from that star has been travelling toward you since around the year 1900, before the first aircraft ever left the ground. As it passes through the atmosphere of that planet, a handful of molecules absorb a fraction of specific wavelengths. Those molecules may be the chemical byproduct of living things metabolizing sulfur in an alien ocean. The light continues traveling, arrives here, falls on a mirror 1/5 the width of a swimming pool, cooled to temperatures colder than Pluto's surface, hovering in permanent darkness behind the Earth. And in those photons, in those specific dimmed wavelengths, is the faintest possible chemical record of what that atmosphere contains. Webb reads it. That is not metaphor. That is the actual mechanism, the actual physics, the actual engineering. A machine built to hear a whisper from a world we will never visit, carrying a chemical message that we are only now, for the first time in human history, capable of reading. The precision required is not incidental to the story of K2-18b. The precision is what makes the story possible at all, but precision has boundaries, and honesty requires acknowledging them. A 3 sigma result means something. It is not noise, but it is also not certainty. The same data that produces a confident signal in one team's analysis produces ambiguity in another's. The same instrument that detected dimethyl sulfide in K2-18b's atmosphere also introduced systematic uncertainties that rival teams have spent months trying to characterize. The mid-infrared range where MIRI operates is technically the most demanding regime of Webb's capabilities, and the most prone to instrumental artifacts that can mimic molecular signals if not handled carefully. This is the honest position. The molecules may be there, the signal is real enough to publish, real enough to debate, real enough to demand follow-up observations. But the instrument and the technique both carry limitations that the signal is currently sitting inside, not clearly above, which raises a question that goes beyond the technology entirely. If even the best instrument humanity has ever built, operating at the edge of physical possibility, in the coldest and most isolated location we have ever placed a scientific instrument, produces results that the scientific community still cannot unanimously agree on, what does that tell us about what we are trying to answer? The question of whether K2-18b carries life is not simply a technical question. It is a question about how science handles its own uncertainty, about what level of evidence is enough to say something true, about what happens when the most extraordinary possible conclusion and the most cautious possible interpretation are both consistent with the data. The scientists working on this are aware of the weight of what they are doing. They have been working with that weight for years, and the debate they are having openly in published papers, at conferences, in preprints and rebuttals and counter-analyses is one of the most consequential scientific arguments of our lifetimes. Because one side of that debate, if it is right, changes everything we thought we knew about our place in the universe. And the other side, if it is right, tells us that we have not yet built something capable of hearing clearly enough. Either answer demands a response, and science, to its credit, gave one. Not quietly, not behind closed doors, publicly, rigorously, and with the full weight of competing teams, rival analyses, and uncomfortable data brought into the open. Because the most important moment in science is not the moment a discovery is announced. The most important moment is the one that comes immediately after, when every other scientist in the field picks up the same evidence and tries, with genuine effort, to prove it wrong. That is what happened to K218b, and understanding what that process looked like, what it found, what it didn't, and where it stands today is the only honest way to understand what this planet actually means. Let's be precise about what scientific scrutiny actually requires, because the word debate can sound like disagreement between equals who simply see things differently. What happened with K218b was more structured, more demanding, and more important than that. When the Cambridge team, led by Niku Madhusudan, published their 2025 result claiming a 3 sigma detection of dimethyl sulfide in K218b's atmosphere, they were not simply announcing a finding, they were submitting that finding to a process designed over centuries of scientific practice to dismantle it. Every claim in science survives only by failing to be destroyed. A result that cannot be attacked from multiple angles, that has no alternative explanations, that holds up under every form of scrutiny a community of intelligent, skeptical professionals can devise. That result, and only that result, earns the right to be called robust. The Cambridge team knew this. They had spent extended time before publication attempting to demolish their own conclusion. That is not modesty. That is methodology, and it matters enormously to understanding the significance of what follows. The team began with the most obvious alternative explanation: geology. K218b orbits a star. That star's system presumably has a geological history. And planets with geological activity, volcanoes, hydrothermal systems, tectonic processes, produce sulfur-bearing compounds. Sulfur dioxide, hydrogen sulfide, sulfuric acid. Could volcanic chemistry on K218b produce dimethyl sulfide, or a compound so chemically similar that Webb's instruments couldn't tell them apart? The answer, based on careful spectral analysis, was no. Volcanic sulfur compounds produce absorption signatures at specific wavelengths that do not match the fingerprint Webb detected. The dimethyl sulfide signal and volcanic sulfur signals are chemically distinct, as distinct in spectral terms as two different musical notes played on different instruments. The team compared the wavelengths precisely. The match to dimethyl sulfide held. The match to volcanic sulfur did not. Geology ruled out. Next, lightning. Electrical discharges in planetary atmospheres, lightning, can drive chemical reactions that produce molecules that would not otherwise form. In certain laboratory conditions, lightning-like discharges through gas mixtures produce organic compounds including simple sulfur-bearing molecules. Could lightning in K218b's hydrogen-rich atmosphere synthesize dimethyl sulfide at detectable levels? The team ran the numbers. Lightning-driven synthesis is real, but extraordinarily inefficient. The rate at which lightning produces any given compound in an atmosphere is many orders of magnitude below what would be needed to accumulate dimethyl sulfide at the concentrations Webb detected. Orders of magnitude is a precise term. 1 order of magnitude means 10 times. Several orders of magnitude means millions of times. The lightning mechanism produces vastly too little. Not barely too little. Not close, but insufficient. but off by a factor so large it effectively rules the pathway out as a primary source. Lightning ruled out. Then hydrothermal chemistry, the possibility that mineral-rich hot water circulating through rock, the way Earth's hydrothermal systems work, could drive the production of dimethyl sulfide without any biology involved. This one was more nuanced. Hydrothermal systems on Earth do produce trace amounts of sulfur-bearing organic compounds, but the step that produces dimethyl sulfide at biologically relevant concentrations requires specific biochemical enzymes, molecular machines that living cells manufacture and deploy specifically for this reaction. Without those enzymes, the hydrothermal pathway stalls, the chemistry doesn't complete itself, and on a world where no life has yet been confirmed, assuming the presence of biological enzymes to explain a biosignature is circular reasoning. The chemistry simply doesn't get there on its own. Hydrothermal chemistry ruled out, and then the team turned to the instrument itself. Every scientific instrument introduces noise, systematic errors, calibration drift, electronic artifacts that can mimic a real signal if not handled carefully. The most important check on any spectroscopic detection is whether the signal survives analysis by independent teams using different software, different calibration assumptions, and different mathematical methods for removing instrumental noise. The Cambridge team ran multiple independent analysis pipelines on the Webb data. The dimethyl sulfide signal appeared across those pipelines, not with identical strength, but consistently in the same place, at the same wavelengths, at a confidence level that survived the variations in how the data was processed. That consistency is meaningful. Instrumental artifacts tend to behave differently depending on how you process the data around them. A real molecular signal tends to persist. But here is where the story cracks open, because other teams were not idle. In July 2025, a team led by Renyu Hu at NASA's Jet Propulsion Laboratory, one of the most respected planetary science institutions on Earth, published a reanalysis of the same JWST data, the same raw observations, the same numbers that came off Webb's detectors. Their conclusion was different. The JPL team found that when they applied their own calibration methodology and noise removal approach to the mid-infrared data, the evidence for dimethyl sulfide became statistically inconclusive, not absent, inconclusive. The signal did not disappear entirely, but it fell below the threshold where they were willing to characterize it as a confirmed detection. Their analysis attributed the apparent signal, at least in part, to systematic noise patterns in the MIRI mid-infrared instrument, patterns that, without extremely careful handling, could produce false molecular signatures. Then, in August 2025, a separate study by a team including Kevin Stevenson concluded that what they called red noise, a specific type of correlated noise in time series data, where errors are not random but cluster together in ways that can mimic real signals, contaminated the mid-infrared observations. This type of noise is particularly insidious. Random noise averages out when you stack multiple observations. Correlated noise does not. The more data you accumulate, the more stubborn the false signal becomes. The Stevenson team's reanalysis confirmed one result from the original detection clearly: methane at 4 sigma confidence. Methane was real, but their analysis found no statistically significant carbon dioxide, no statistically significant dimethyl sulfide, just methane and systematic noise in the longer wavelength data that had been interpreted as something more. The same data, processed differently, different conclusions, and then the lab results arrived. In 2024, a separate group of researchers published a laboratory experiment demonstrating that dimethyl sulfide can form abiotically without biology when certain gases are exposed to ultraviolet light in conditions designed to simulate the atmosphere of a sub-Neptune exoplanet. Abiotically, without life. The yield was small, the conditions were specific, The pathway requires particular atmospheric chemistry that may or may not match K2-18b precisely. But the pathway existed, and it got stranger still. Astronomers searching comets and the interstellar medium, the vast clouds of gas and dust between the stars, had already detected dimethyl sulfide outside of biological contexts, in the frozen material of comets travelling through our solar system, in regions of space where no planet exists, let alone a living ocean. Dimethyl sulfide was not, it turned out, a molecule found only in the presence of life. Exclusively in the biology of Earth's oceans, yes, at the scale needed to fill an atmosphere. But elsewhere in the universe, at trace levels, through non-biological chemistry, it had been seen before. The ground was shifting, the molecule wasn't unique to life, the signal was contested, the instrument was imperfect, the data was real, but the interpretation was not settled. And then NASA said something that clarified exactly where this stood. NASA's official position on K2-18b has been consistent and careful. A single biosignature detection, even a confirmed one, would not, in NASA's assessment, constitute the discovery of life. That statement is not pessimism. It is philosophy of science made explicit. To claim the discovery of life from a chemical signal requires ruling out not just the obvious non-biological explanations, but all plausible ones. It requires independent confirmation from multiple instruments and methods. It requires the signal to be so strong, so consistent, and so impossible to explain without biology, that the biology explanation is the only one standing. In particle physics, the threshold for announcing a fundamental discovery, such as the Higgs boson in 2012, sits at 5 sigma. That means a probability of roughly 1 in 3.5 million that the result is noise. K2-18b's dimethyl sulfide detection sits at 3 sigma, less than 1 in 300 probability of being random noise, meaningful, scientifically significant, worthy of serious attention and follow-up, but not 5 sigma, not a discovery. And that gap between 3 sigma and 5 sigma is exactly where the most consequential debates in science tend to live. Close enough to be real, not close enough to be certain. Let's be honest about what this means. The Cambridge team has not been shown to be wrong. Their signal has not been debunked. Alternate explanations have not conclusively replaced the biological one. The detection stands as the strongest possible hint of a biosignature ever recorded in an exoplanet atmosphere. The honest position, the one that respects both the signal and the uncertainty, is precisely that. The strongest biosignature hint ever recorded. Not confirmed life, not dismissed noise, a hint that demands more investigation and refuses to disappear. And this, precisely, is how science should operate. Publicly, messily, with competing teams pointing at the same evidence and reaching different conclusions, forcing each other to be more precise, more careful, and more honest about what the data actually says. The debate over K2-18b is not a failure of science. It is science functioning at its most rigorous, at the edge of what our instruments can measure and what our methods can resolve. The fact that it remains unresolved is not a weakness. But there is something in this debate that almost nobody talks about. Something that sits quietly behind all the instrument arguments, the sigma thresholds, the noise analyses, and the competing pipelines. K2-18b orbits a red dwarf, a star that burns so slowly, so efficiently, so patiently, that it will still be burning billions of years after our own sun has exhausted its fuel and collapsed. If life exists in K2-18b's ocean, if the signal is real and the interpretation holds, that life has access to an almost incomprehensible duration of stable, consistent energy, time measured not in billions of years but in trillions, the implications of that single fact reshape everything the debate is actually about. Because we are not just asking whether K2-18b has life now. We are asking whether this class of star, the most common type of star in the entire galaxy, making up roughly 75% of all stars in the Milky Way, routinely hosts the conditions for life that lasts. Not briefly, not for a few billion years the way complex life on Earth has existed, but for durations so vast they have no human name. And to understand what that means for K218b and for every world like it, we need to understand the star itself, not as a backdrop, as the engine, the ancient, patient, extraordinarily long-lived engine that makes any of this possible. The star is not a backdrop. It never was. Everything about K218b, its temperature, its orbit, its atmospheric chemistry, the very possibility that something biological could persist in its ocean, traces back to the star it orbits. And that star turns out to be one of the most extraordinary objects in the galaxy, not because it is large or bright or dramatic, for the opposite reason entirely. K218 is small, cool, dim, and because of that, it will outlive almost everything else in the universe. Let's put K218 beside our Sun so the contrast lands properly, because the numbers here are striking in a very specific way. Our Sun burns at a surface temperature of approximately 5,778 Kelvin. Kelvin is the scientific scale for temperature. 0 Kelvin is absolute zero, the coldest anything can ever be, and each degree Kelvin above that represents the same step as 1 degree Celsius, above minus 273. At 5,778 Kelvin, our Sun glows white-yellow, pouring out light across the full visible spectrum, warming a planet 93 million miles, about 150 million kilometers away. K218 burns at somewhere between 3,457 and 3,645 Kelvin. That is nearly 40% cooler than our Sun. A surface that cool does not emit white-yellow light. It emits deep red, the color of a heating element on a stove just before it reaches full temperature. The color of embers, not flame. The mass of K218 sits between 41 and 49% of our Sun's mass, less than half as heavy, less than half the fuel, less than half the gravitational compression at the core, and its luminosity, the total energy it radiates in every direction, amounts to just 2.34% of our Sun's output. Not slightly dimmer, 43 times dimmer, 2.34%. If our Sun were a floodlight illuminating a football field, K218 would be a single candle at the center. That is the star K218b orbits, and that extraordinary dimness is precisely why this story exists. Here is what most people intuitively understand about stars, and why that intuition leads to the wrong conclusion about red dwarfs. We tend to think of stars as burning, consuming fuel rapidly, blazing intensely, and eventually running out. Our Sun confirms this intuition. Formed roughly 4.6 billion years ago, our Sun has used up approximately half its hydrogen fuel, and has perhaps 5 billion years remaining before it exhausts its core, expands into a red giant, and consumes the inner planets. 10 billion years total, start to finish, bright, productive, and finite. The logic follows naturally. A smaller star must have less fuel, so it must burn out faster. A star with less than half the Sun's mass should be done sooner, right? But this is where the assumption shatters. Not slightly wrong, completely, profoundly wrong. And the physics behind why reveals something extraordinary about what red dwarfs actually are. Inside our Sun, the process of turning hydrogen into helium, the nuclear fusion that powers every star, happens exclusively in the core, a dense, hot central region that makes up roughly 35% of the Sun's total volume. The rest of the Sun's interior is, in one sense, inert, structural mass that surrounds the core, channeling heat outward, but not participating in the fusion itself. This means our sun burns only a fraction of its total hydrogen. The hydrogen in the outer layers never mixes down into the core. It never reaches the temperatures and pressures needed for fusion. When the core hydrogen runs out, the outer layers cannot replenish it. The sun's burning is inefficient, like a furnace that can only use fuel from one specific shelf, while identical fuel sits untouched on every other shelf in the room. Red dwarfs work differently. Fundamentally, structurally differently. A red dwarf with mass below a certain threshold, roughly around 35% of the sun's mass, though the boundary varies, has a fully convective interior. Convection means mixing. The entire interior of the star continuously circulates, like a pot of boiling water where hot material rises from the bottom, cools at the top, and sinks again in a constant, churning cycle. In a fully convective star, hydrogen from the outer layers continuously cycles inward toward the core. New fuel is always arriving. Old processed helium is always being redistributed. Nothing sits unused. The result is extraordinary efficiency. A red dwarf doesn't burn through a fraction of its hydrogen. It burns through nearly all of it. Every hydrogen atom in the entire star eventually participates in fusion, not just the ones that started in the core. More available fuel, burned more completely, at a much lower rate. The combination produces lifetimes that are genuinely difficult to hold in the human mind. K2-18 itself sits at approximately 41 to 49% of the sun's mass, right at the edge of what models suggest may be the fully convective zone for red dwarfs, and its specific interior structure is not yet precisely resolved. But the broader class it belongs to, the M-dwarf family of stars, contains members with masses as low as 8 or 9% of the sun's, and for the smallest red dwarfs, the calculated lifespan reaches upward of 10 trillion years. 10 trillion years. The current age of the entire universe is approximately 13.8 billion years. That is 13,800 million years. 10 trillion years is roughly 725 times the current age of the universe. The smallest red dwarfs have not even reached the first 1% of their total lifespan. Think about what that means physically. Every red dwarf visible in the sky tonight, every one of the dim, cool, almost invisible stars that make up the vast majority of stars in our galaxy, has barely started burning. The universe is, in a sense, a young place, still near its beginning. These stars are in their infancy. They will be burning steadily, reliably, for durations so vast they encompass the entire current age of the universe hundreds of times over. K2-18 itself is estimated to be between 2.4 and 3.1 billion years old, younger than our Sun. But even with that head start, K2-18 almost certainly has hundreds of billions of years of stable burning remaining, perhaps longer. Not 5 billion years the way our Sun does. Not 10 billion, hundreds of billions, at minimum. Any life that may exist in K2-18b's ocean is not racing against an expiring clock. The clock has barely started. Let's consider what evolutionary time actually produces, because the numbers above only land if we understand what billions of years of stable conditions do to life. Earth is 4.54 billion years old. The oldest confirmed microbial life on Earth dates back at least 3.5 billion years. Single-celled organisms, bacteria, the simplest biological forms we know. For roughly the first 3 billion years of life on Earth, that is all that existed. Nothing multicellular, nothing with eyes or limbs or behavior, just chemistry that reproduced itself in ancient shallow seas. Complex animal life, creatures with bodies, organs, nervous systems, didn't appear until roughly 540 million years ago, in the period scientists call the Cambrian explosion. 540 million years ago out of 4 billion years of life on Earth. Life needed 3 billion years of practice before it attempted complexity. Humans, the species capable of building telescopes and reading the sky, appeared less than 300,000 years ago, a fraction of a percent of Earth's history. Now consider K218b. Whatever life may exist in its ocean, if it exists at all, has been sitting in stable, consistent, chemically rich conditions under a steady star for somewhere between 2 and 3 billion years already. And unlike Earth, whose sun will exhaust its fuel and destroy the inner solar system in roughly 5 billion years, K218b faces no such deadline for hundreds of billions of years more. The question is not just whether K218b could host life now. The question is what life in a stable ocean, under a patient star, with hundreds of billions of years available to it, might eventually become. Earth got 300,000 years of intelligent, tool-using, sky-reading life before building Webb. K218b's timeline, if life is there, extends so far beyond ours that imagining its end is genuinely beyond the capacity of human intuition. That is not speculation. That is simply what the physics of a low-mass, fully convective star produces. But red dwarfs carry a complication that the outline of their lifetimes doesn't immediately reveal. Young red dwarfs can be violently active. In their early lives, they produce intense bursts of ultraviolet and X-ray radiation, stellar flares that, for a planet orbiting as close as K218b does, could in principle strip an atmosphere, irradiate a surface, or disrupt the chemistry needed for life. This is one of the genuine unresolved debates in the habitability of red dwarf planets. The early bombardment of high-energy radiation may make the first billion years of a planet's life around such a star difficult. K218, however, appears to be in a relatively quiet phase of its stellar life. Based on current observations, it shows comparatively low activity levels for its class, fewer and weaker flares than many M-dwarfs of similar age. This makes two things easier simultaneously. First, it makes K218b's atmosphere more likely to have survived intact. Second, it makes K218b's atmospheric observations cleaner, less stellar noise contaminating the spectral data Webb is reading. A quieter star produces cleaner science, and cleaner science is part of why K218b became the most promising candidate, rather than other red dwarf planets that exist closer and are nominally easier to study but whose stars are far more active. The signal Webb found in K218b's atmosphere was hard enough to read with a relatively quiet star in the way. A more active star would have made it effectively impossible. Here is the piece of this story that changes the scale of everything we have been discussing. Red dwarfs, the class of star K218 belongs to, constitute approximately 75% of all stars in the Milky Way. 3 out of every 4 stars in our galaxy are red dwarfs. Not rare, not exotic. The single most common type of stellar object that exists, and approximately 80% of M-dwarf stars, the spectral category that includes K218, appear to host planets in their habitable zones based on current survey data. Not 8%, 80%. The Milky Way contains roughly 200 to 400 billion stars. Roughly 75% of those, somewhere between 150 billion and 300 billion, are red dwarfs. 80% of those host habitable zone planets. The math produces a number so large it stops meaning anything without a translation. Somewhere between 120 billion and 240 billion planets in the habitable zones of red dwarfs, in our galaxy alone, each one potentially orbiting a star with hundreds of billions of years of stable fuel remaining. K218b is not an anomaly. K218b may be representative. One example of a class of worlds so numerous that if even a small fraction of them carry what K218b may carry, the galaxy is not a quiet, empty expanse of rock and gas, punctuated by rare biology. The galaxy may be, in the most understated possible terms, inhabited. That is what the physics of this star implies, not what the molecules in K218b's atmosphere have proven. What the star's nature, combined with its prevalence, suggests is possible. And this is where the story of K218b stops being a story about one planet, one star, one contested chemical detection, if red dwarfs are this common, if habitable zone planets around them are this common, if the conditions for Hycean worlds, global oceans under hydrogen atmospheres, around stable low-mass stars are not rare but routine, if the chemical signals Webb detected in K218b's atmosphere are real and biological, then the question we have been circling since the first detection of a water vapor in K218b's sky in 2019 is not actually a question about K218b at all. The real question is this: if chemistry produces life wherever conditions allow, and the conditions we see at K218b exist across hundreds of billions of worlds, what does that say about the universe we live in? What does it say about our place in it? 60 years ago, a radio astronomer named Frank Drake sat in a room at Green Bank, West Virginia, and wrote an equation on a blackboard, an equation designed to estimate how many intelligent civilizations might exist in our galaxy. At the heart of that equation sat a variable that Drake had no way to estimate, no data for, no constraint on at all: the probability that life emerges on a habitable world. For 60 years that variable remained blank, a placeholder, an honest admission that we simply did not know. K218b may have just written something in that blank space for the first time, not the answer, the first number. Frank Drake wrote an equation on a blackboard in Green Bank, West Virginia in 1961, and for 60 years, one variable in that equation sat blank, not because scientists forgot to fill it in, but because nothing in the observable universe had ever given them a number to put there. K218b may have just changed that, not with certainty, not cleanly, but for the first time in the history of this question, the blank space has something written in it. And what that means, for planetary science, for our understanding of life, and for what we are building next, is a shift so large it is genuinely difficult to absorb all at once. Let's spend a moment with Drake's equation, because it is one of the most honest scientific documents ever written, and the most honest thing about it is what it could not answer. Frank Drake designed his equation not to produce a result, but to organize a question. The question: how many communicating civilizations might exist in our galaxy right now? The equation multiplied together a chain of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets in habitable zones, the fraction where life actually emerges, the fraction where intelligence develops, the fraction that builds detectable technology, and how long those civilizations survive. Multiply those fractions together across the hundreds of billions of stars in the Milky Way, and you arrive at an estimate. But here was the problem Drake acknowledged openly at the original Green Bank conference where he presented it. Most of those variables had real, measurable values, or at least reasonable estimates. The rate of star formation was knowable from astronomical surveys. The fraction of stars with planets had been unknown in 1961, but became measurable after Kepler. The fraction of habitable zone planets was becoming clearer, but one variable, the probability that life actually emerges on a world where conditions allow, had no data. None. Zero. Scientists could not put a real number on it because before K218b, we had only ever observed life on one world, Earth. And you cannot calculate a probability from a sample size of 1. A sample size of 1 tells you that life happened at least once. That is all it tells you. For 60 years, astronomers filling in Drake's equation had to either leave that variable blank, set it to 1, meaning life always emerges wherever conditions allow, or set it to something vanishingly small, meaning Earth was a fluke so extraordinary it bordered on miraculous. Either extreme was defensible, neither had data. K218b doesn't fill the blank completely, but it does something mathematically important. K218b sets a flaw. A flaw in probabilistic terms is the minimum value something can take. If K2-18b's atmospheric signals are biological, and that remains contested as we have followed carefully, then life emerged at least twice in the observable universe, on Earth and in the ocean of a world 124 light-years away. Two independent origins in different stellar systems, around different types of stars, in different atmospheric conditions. Two data points is not a sample size that allows confident statistics, but 2 data points does allow one calculation that one does not. It eliminates 0. The probability of life emerging on a habitable world cannot be 0, because if it were 0, we would not exist to ask the question. But beyond Earth, if K2-18b carries biology, the probability is not vanishingly small either. The universe managed it again, under quite different conditions, around the most common type of star, on what may be the most common type of potentially habitable planet. That is the flaw. And a flaw, in mathematics, is not a small thing. It changes the character of every calculation built on top of it. Let's put the numbers through Drake's logic informally, not as a precise calculation, but to feel the scale of what the flaw implies. Roughly 80% of M-dwarf stars appear to host planets in their habitable zones. Red dwarfs constitute approximately 75% of all stars in the Milky Way. The galaxy contains somewhere between 200 and 400 billion stars. If even 1% of those habitable zone planets around red dwarfs host something analogous to K2-18b, oceans, chemistry, biological signals, the Milky Way contains not millions but billions of living worlds. Billions, not spread uniformly through the galaxy, not accessible, not detectable with current instruments, but there, present, running their chemistry, breathing molecules into hydrogen skies above endless oceans, orbiting patient dim stars that will still be burning when our own sun is a cold cinder. Here is the thing most people don't realize about what K2-18b implies at a deeper level. Humanity has experienced 2 previous moments in the history of science where our understanding of our place in the universe fundamentally contracted. Both times the scientific community resisted. Both times the resistance eventually gave way to the evidence. The first was Copernicus, the heliocentric model, Earth orbiting the Sun, not the Sun orbiting Earth, removed humanity from the physical center of the cosmos. We had assumed, intuitively and theologically, that we occupied the central point. We did not. We orbited. We were peripheral. The universe had no center that was ours. The second was Darwin. Natural selection removed humanity from a special originating event. The idea that we were deliberately, separately, purposefully created. We were not. We descended. We were continuous with every other organism that had ever lived on Earth, sharing common ancestors with the bacteria in the soil and the fish in the sea. Our origin was chemistry and time and pressure, not intention. Each demotion felt at the time like a loss, and each one turned out to be something else, an expansion, a realization that the universe was larger, older, more capable, and more interesting than the story centered on us had room for. K2-18b presents the third demotion, not of our location, not of our origin, of our exclusivity. The implicit assumption beneath 60 years of unanswered searching for extraterrestrial life was that life, if it exists elsewhere, is rare, a lucky accident, a miracle of timing and chemistry that happened once, on this particular rock, and possibly happened again somewhere in the vast darkness, but probably didn't. The silence of the cosmos seemed to support this. We had listened for signals. None came. We had searched for biology in our solar system. Nothing unambiguous emerged. K2-18b suggests the silence may not mean absence. The silence may mean we were looking the wrong way, with the wrong tools, for the wrong signals, around the wrong type of star. And now that we have finally looked correctly, what appears in the data is not nothing. The deepest implication of K2-18b, the one that sits beneath all the instrument arguments and sigma thresholds and competing analyses, is this. If life exists in K2-18b's ocean, it did not require a miracle. The conditions there are common. Hydrogen atmospheres are common. Global oceans are, according to the Hycean model, likely common. Red dwarf stars are extraordinarily common. The chemistry that Webb detected, sulfur compounds, carbon gases, depleted nitrogen, is not exotic. It is what chemistry does. It is what happens when the right elements interact over sufficient time under stable conditions. Life, in that case, is not an event, not a singularity, not a one-time accident in an otherwise sterile cosmos. Life would be what chemistry does when given enough time and the right environment, a property of matter expressed wherever the conditions allow, not common like oxygen in the air, but common like reefs in warm, shallow water, not everywhere, but in the places where the conditions are right, almost inevitable. This is a reframing so profound it is difficult to hold in one thought. The universe has been running chemistry for 13.8 billion years, on billions of worlds, in billions of oceans, under billions of patient, dim, long-burning stars. If chemistry reliably produces life, the cosmos is not silent. The cosmos has been generating life for most of its history, on most of the worlds where the conditions allow, without announcement and without our awareness. We were simply too young to know it, too limited in our tools to read it, too certain that what we knew from one world was the only form it could take. And now, the instruments are changing rapidly. K2-18b did something beyond producing a contested detection of dimethyl sulfide. It proved the technique works. Transmission spectroscopy with Webb's instruments, trained on a Hycean world, produces readable chemical data. The signal is faint and the interpretation is still debated, but the data is there and the method is real. That proof of concept changes everything about what comes next. The ESA aerial mission, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, is scheduled to launch in 2029. Ariel is not designed to study one exoplanet or 50. Its survey target is approximately 1,000 exoplanet atmospheres, characterized systematically, with consistent methodology, across a broad range of planetary types. 1,000 atmospheric fingerprints, a catalogue, not a case study. A statistical picture of what planetary atmospheres across the galaxy actually contain. If K2-18b type chemical signatures appear in 10 of those 1,000 atmospheres, that is a pattern. If they appear in 50, it is a prevalence. If they appear in 200, it changes the answer to Drake's missing variable in a way that is no longer contestable. The extremely large telescope, currently under construction in the Atacama Desert in Chile, with a primary mirror spanning 39 meters across, about 128 feet, will add a capability Webb does not have: 39 meters. To put that in perspective, the main mirror of Webb spans 6.5 meters, not quite 22 feet. The ELT's mirror is 6 times wider, meaning it collects roughly 36 times more light per unit time. That light-gathering power allows something new: the measurement of isotopic ratios in exoplanet atmospheres. Isotopes are slightly different versions of the same atom, same element, different mass. The ratio of certain isotopes in a planetary atmosphere can serve as a fingerprint of biological versus non-biological chemistry, because life preferentially selects certain isotopic forms in ways that geology alone does not. The ELT may allow scientists to read not just what molecules are present in K2-18b's atmosphere, but whether those molecules were made by something alive. The Nancy Grace Roman Space Telescope, also approaching launch, carries wide-field survey capability that will inventory thousands of planetary systems statistically, building the population-level picture of how many worlds exist, at what distances, around what types of stars, in what configurations. Roman will not read atmospheres, but it will tell us how many targets to point the atmospheric readers at. And threading through all of this, machine learning systems trained on Webb's existing spectroscopic data are already accelerating the analysis pipeline. The same kind of pattern recognition tools that identify faces in photographs and voices in noise are being applied to exoplanet spectra, learning to recognize molecular signatures faster, more accurately, and across larger data sets than human analysis teams alone can process. The era of finding 1K2-18b is ending. The telescope pointed, the transit observed, the spectrum read, the paper written, the debate begun. One world, years of work, contested results. That era is closing. The era opening is different in kind, not just in scale. Not one atmosphere read with difficulty, but hundreds read systematically. Not one contested detection, but a catalogue of biosignature candidates ranked by confidence. Not one team debating one result, but a field producing statistics about how common certain chemistry is across the galaxy. The question changes. It stops being, did Webb detect something biological at K2-18b? It becomes, across the nearest 1,000 habitable zone planets, what fraction of them carry chemistry that cannot be explained without life? That is a different kind of science, the same rigor, the same demand for evidence, but operating at a scale that produces answers rather than debates. K2-18b also did something permanent to planetary science itself. Before K2-18b, planetary science had two categories for worlds, rocky and gaseous. A planet was either solid to the core like Earth or a vast sphere of compressing gas like Jupiter. Every exoplanet discovered fit, imperfectly or well, into one of those boxes. K2-18b required a third box, Hycean worlds, ocean-covered surfaces beneath hydrogen-helium atmospheres, around red dwarf stars, in habitable zones with global chemistries potentially compatible with life. The box was invented because the planet demanded it, and now that the box exists, the question of how many worlds belong in it, how prevalent Hycean worlds are in the galaxy relative to rocky worlds or gas giants, is a question with a framework to answer it. Early indications from survey data suggest Hycean worlds, or sub-Neptune planets in general, may actually be more common than rocky Earth-like planets. Not rare, typical. If that holds, and it is not yet confirmed at the level of certainty planetary scientists require, then the most common habitable environment in the galaxy is not an Earth, not a rocky world with a thin nitrogen-oxygen atmosphere and liquid water in isolated ocean basins surrounded by continents. The most common habitable environment may be a world covered entirely by water, wrapped in hydrogen, orbiting a dim patient star, a world nothing like ours in almost any physical particular. And yet, if K2-18b's chemistry means what the Cambridge team believes it means, a world that does what Earth does, make life. 60 years ago, Drake wrote an equation. At the heart of it, a blank, a variable with no data, the probability that life emerges on a habitable world. K2-18b has not filled that blank, but it has written the first number in the margin beside it. Not 0, not 1, something between them, uncertain but real, visible for the first time in a spectrum of light that left an alien sky 124 years ago and arrived at 18 gold mirrors in the cold darkness behind the Earth. The question this number raises is not purely scientific. It is not answered by more spectra or better telescopes or higher sigma values, though all of those matter. The question it raises is one humanity has been circling for as long as we have been capable of asking it. If we are not alone, if life is what chemistry does, and the chemistry runs on billions of worlds around billions of patient stars, What does that say about what we are doing on this one? A world capable of building Webb. A world capable of reading the atmosphere of an alien ocean from 124 light years. A world that, at this exact moment in its history, is systematically destabilizing the atmospheric chemistry of its own planet, while simultaneously building instruments sensitive enough to read the atmospheric chemistry of another one. That paradox is not abstract. It is the defining tension of this moment. And what K2-18b reveals about the universe and what we do with that revelation are questions that belong to the same story. The light that arrived at Webb's mirrors left K2-18b in the early 1900s, when the first powered aircraft had barely left the ground, when the concept of an exoplanet was not yet imaginable, when the idea that we might one day read the chemistry of another world's sky was the exclusive territory of speculation. That light had been travelling all that time, waiting in a sense for us to be ready to read it. The light had already been waiting. That was the quiet truth at the end of everything we have followed. The light that carries K2-18b's atmospheric chemistry left that world approximately 124 years ago and travelled through the dark in silence, arriving precisely when we had, for the first time in the history of this planet, built something capable of reading it. But now we have to sit with the full weight of what that means, because the species that built the instrument, the species that spent 25 years and the combined intellectual effort of thousands of engineers, scientists and mathematicians from 14 countries, is also the species currently running the most consequential uncontrolled chemistry experiment in the 4 billion year history of its own planet's atmosphere. And those two facts belong in the same sentence, not one after the other, together. Let's start with what Earth's biosphere actually is, because the word gets used so often it loses its meaning. The biosphere is not just the collection of living things on Earth. Plants, animals, bacteria, fungi, that is part of it, but only part. The biosphere is the system that living things and the physical Earth have built together over 4 billion years of continuous interaction. A system where life modifies the chemistry of the atmosphere, the oceans and the soil. And the atmosphere, oceans and soil modify what kinds of life can exist, in a feedback loop so ancient and so finely balanced that the result, over geological timescales, looks less like accident and more like regulation. 4 billion years ago, Earth's atmosphere contained almost no free oxygen. The sky was a mix of nitrogen, methane, carbon dioxide and other gases produced by geological processes. Volcanoes, outgassing from the cooling crust, photochemical reactions driven by sunlight. A human transported to early Earth would suffocate within minutes. There was simply nothing breathable in the air. Then life began. First as simple single-celled organisms in the ancient shallow seas, consuming the available chemistry around them, growing, replicating, dying. And then, roughly 2.4 billion years ago, in what geologists call the Great Oxidation Event, photosynthetic bacteria began releasing oxygen into the atmosphere as a metabolic byproduct, a waste product essentially, of turning sunlight and carbon dioxide into energy. Oxygen accumulated, slowly at first, then faster, as more and more photosynthetic life spread across the surface of the planet. The composition of Earth's atmosphere today, approximately 78% nitrogen, 21% oxygen, and 1% of everything else, is not a geological fact. It is a biological fact. Life made it. Over 4 billion years, the biosphere built the air we breathe from the chemistry available to it, and then maintained that composition against the forces that would otherwise alter it. When volcanic activity releases carbon dioxide, biological processes, the growth of plants, the absorption by ocean organisms, the cycling through soils, pull it back down. When oxygen rises too high, the increased flammability of forests limits the overproduction. The system self-regulates, not by intent, by the physics and chemistry of what organisms do when they are numerous, diverse, and operating at scale. This is extraordinary, and it is the context in which K2-18b's atmospheric signals become not just interesting, but profound. The atmospheric chemistry Webb detected in K2-18b's sky: methane present, carbon dioxide present, carbon monoxide absent, ammonia depleted, and the possible presence of dimethyl sulfide, is not, if the biological interpretation holds, a random assortment of molecules. It is the signature of a system that, like Earth's biosphere, is actively processing the chemistry available to it, taking certain molecules in, releasing certain molecules out, maintaining concentrations that dead chemistry alone would not produce and would not sustain. The absence of carbon monoxide, which dead hydrogen-rich chemistry should produce, suggests something is consuming it or preventing its accumulation. The depletion of ammonia suggests something is incorporating nitrogen. The possible presence of sulfur-bearing biological compounds suggests something is metabolizing sulfur in the ocean below. Each signal, taken alone, is contestable. Together, they describe what a living ocean does to an atmosphere over billions of years. Not quickly, not dramatically. Through the patient, continuous, enormously scaled operation of organisms whose individual lives are invisible and whose collective effect is a planetary signature readable from 124 light-years away. This is what Earth's biosphere has been doing for 4 billion years, quietly, continuously, without announcement. And then, in approximately the last 250 years, a period so short relative to Earth's biological history that it is, in geological terms, essentially instantaneous, one species began altering that system in a direction no biological process had previously taken it. Not slowly, not in geological time, in the span of a few human generations. Here is the collision that this story has been building toward. Not manufactured, not rhetorical, physically, chemically real. The same cognitive capacity that allowed human beings to design Webb's mirror segments to nanometer scale precision. The same capacity for abstraction, pattern recognition, and long-range planning that produced 25 years of coordinated international engineering effort also produced the industrial systems that are, right now, altering the concentration of carbon dioxide in Earth's atmosphere faster than at any point in at least the last 800,000 years of our planet's geological record. We know this because we measure it, with instruments, carefully. The same scientific culture that built Webb and reads K2-18b's spectrum reads Earth's atmospheric chemistry with equal precision and finds in the data a signal as clear as any Webb has detected. Carbon dioxide rising at a rate the natural carbon cycle cannot absorb quickly enough to maintain the balance Earth's biosphere took 4 billion years to build. Earth's biosphere maintained regulated atmospheric balance for 4 billion years before industrial disruption. K2-18b's atmospheric signals, if the biological interpretation is correct, suggest a biosphere of comparable age and maturity, one that has been running its chemistry, maintaining its balance, for billions of years under a patient red star with no technological species capable of disrupting it from within. We are, right now, the only known example in the observable universe of a technological species actively destabilizing the atmospheric chemistry of the biosphere that produced it, while simultaneously reading the atmospheric chemistry of another biosphere 124 light-years away. That is not dread. That is a mirror. And what it reflects is something that deserves to be looked at directly. The light Webb used to read K2-18b's atmospheric signals left that planet approximately 124 years ago. The exact year it departed depends on when the observation was made. The 2023 and 2025 Webb observations received light that left K2-18b in approximately 1899 and 1901, the very opening years of the 20th century, 1901, 2 years before the Wright brothers lifted a powered aircraft off the ground at Kitty Hawk, North Carolina, for the first time in human history, before any radio broadcast had been transmitted, before the word exoplanet had entered any scientific vocabulary, before the concept that stars other than the Sun might have planets was considered scientifically mainstream, let alone that those planets might harbour detectable atmospheric chemistry. That light left K218b when humanity had not yet left the ground, and it arrived after 124 years of silent travel through the void at the 18 hexagonal gold-coated mirrors of the James Webb Space Telescope, positioned in permanent cold darkness 1.5 million kilometres, about 930,000 miles, from Earth, precisely at the moment when we had, for the first time in human history, built an instrument sensitive enough to read what that light was carrying. The timing is not mystical. The universe does not arrange arrivals for dramatic effect. The light simply travelled, and we simply built the instrument. The fact that both happened in the same narrow window of human capability is a reflection of our age as a technological species, young enough that this is still a first, old enough that we just barely managed it. Think about what that means from another angle. Webb's light-gathering capability required a specific sequence of technological developments: infrared detector arrays, beryllium mirror fabrication, cryogenic engineering, space launch vehicles, orbital mechanics at Lagrange points, and the scientific culture that connected all of those capabilities toward a single purpose across 2.5 decades. Any one of those developments arriving 50 years later would have meant the light from K218b's 1900 atmosphere had already passed through the solar system unread, and we would be waiting for the next transit cycle. We caught it, by the narrowest margin of our own developmental history. We did not build Webb in time to catch that light. We built Webb, and the light had already been waiting. There is a way of describing what happened when Webb's mirrors collected that light that is not dramatic language. It is a physical description of what occurred. For approximately 13.8 billion years, the universe has contained matter, energy, chemistry, and time. For approximately 3.5 billion years, at least one location in the universe has contained life, on Earth. For potentially billions of years, other locations may have contained life as well, running their chemistry quietly in alien oceans under alien skies, with no witness and no record. In 2023, a machine built by one form of life, assembled from the metals of ancient supernovae, powered by solar panels converting the light of our sun, guided by software written by human minds, collected light that had passed through the atmosphere of what may be another form of life, analysed it, found patterns in the molecular absorption, recognised chemical signatures that, on the only other world where we had ever studied biology, could only be explained by biological processes. For the first time in 13.8 billion years, one part of the universe may have recognised life in another, not confirmed, not proven beyond contest, but recognised in the sense that the pattern was read, the question was raised, and the answer, for the first time, was not silence, not absence, not the vast, indifferent emptiness that 60 years of listening had returned, but a signal, faint, contested, scientifically alive, pointing in a direction that nothing in this story has managed to definitively rule out. K218b does not tell us we are special because we are alone. That framing, the one that made every prior silence feel like evidence of our uniqueness, depended on the universe being empty. K218b suggests it is not, and a universe that is not empty tells us something very different about what we are. We are not the exception, we are an expression. One instance of a process the universe runs wherever chemistry, time, and conditions converge. Not rare, not miraculous, not alone. That is not diminishment, that is the opposite of diminishment. The universe does not become smaller or less meaningful because it holds more life. A coral reef does not become less extraordinary because other reefs exist on other coastlines. Life recognizing life across 124 light-years of darkness is not made less remarkable by the possibility that it happens elsewhere, in other oceans, under other stars. It is made more remarkable. We are not looking for proof of life anymore. We are learning to read what was always being written. The molecules were always there. The signals were always traveling. The chemistry was always running in K218b's ocean, in the deep-sea vents of our own planet, in whatever microbial metabolisms may be processing sulfur in alien hydrogen skies, above worlds we have not yet named. We simply lacked the instruments, the patience, the quiet. Webb gave us the quiet. The next generation of instruments will give us the vocabulary. Ariel will give us the catalogue. The extremely large telescope will give us the precision. Roman will give us the numbers. Machine learning will give us the speed. The era of asking whether we are alone is not ending. That question has no final answer from one detection, one world, one contested signal. But the era of asking that question with no data, with no flaw, no number in the margin, no chemical signal from any world but our own to reason from, that era is over. We have a number now, small, uncertain, debated, but real. You have travelled the full distance of this story, from a small, faint dip in starlight noticed by a telescope watching 150,000 stars, to a world with no land and a hydrogen sky, to molecules that should not exist in a dead atmosphere, to a machine colder than Pluto reading a whisper from 124 light-years away, to a scientific war over what the whisper means, to a star that will still be burning when our sun is long gone, to an equation on a blackboard in 1961 that finally has something written in its blank space. And at the end of that distance, there is something that deserves to be said quietly, without building or escalating or pointing somewhere next. The light that Webb caught left K218b in the early 1900s. It travelled in silence through the dark for longer than any human civilization has existed. And when it arrived at a mirror built by human hands, 18 hexagons of gold-coated beryllium, polished to tolerances measured in atoms, assembled by people who spent their working lives making sure that when this light finally arrived, something would be there to receive it. We built that instrument without knowing for certain what it would find. We aimed it at this world because the science suggested something might be there. And when the data came back and the chemistry appeared in the spectrum and the debate began, that debate was not a failure. It was the sound of a species taking seriously, for the first time, the possibility that the universe has been answering a question we have been asking for thousands of years. The cosmos did not begin speaking when Webb caught that signal. The cosmos has been speaking continuously in the language of chemistry and light for 13.8 billion years. We simply, at last, learned to be quiet enough to hear it. At the beginning of this journey, we noted something quiet and simple, that the light Webb used to read K218b's atmosphere left that world in the early 1900s and had been travelling ever since, carrying chemistry humanity couldn't yet read, waiting for an instrument that did not yet exist. That framing was true, but incomplete. The full truth is this: the light was never waiting for us. The universe does not wait. The light simply travelled, as light always does, indifferent to whether anything capable of reading it existed at the destination. It would have passed through our solar system and continued into the dark regardless. It did not know about Webb. It did not know about the 18 mirrors, or the beryllium, or the nanometer tolerances, or the 25 years of work. What changed was not the light. What changed was us. We became, in the space of a single century, the kind of species that could point an instrument at a star 124 light-years away, collect light thinner than a whisper, and find in it the possible breath of another living world. We became, in the span of a few generations, capable of a kind of listening the universe had never seen before, not because the universe had never produced it, perhaps, but because we had never achieved it here until now. The universe was never empty. We were simply too young, too limited, and too alone in our tools to hear what it had always been saying. K218b did not change the universe. K218b changed us. And what we do with that change, on this planet, with this atmosphere, with these instruments and this knowledge and this moment, is the only question left that we have the power to answer. Think about what you just did. You sat down alone, probably at night, and you chose to spend this time with one of the most profound questions the human species has ever asked. Not for a grade, not for work, because something in you needed to know, because the size of the universe matters to you, because the possibility that we are not alone in it matters to you. Webb collected the light, but without a mind willing to understand what that light means, without a human being sitting quietly in the dark, letting the weight of it land, the signal means nothing. The universe spoke. You listened. Both things were required. That is not a small thing. In 13.8 billion years of cosmic history, moments of genuine understanding are rare. You just participated in one. If this moved something in you, if you felt, even for a moment, the profound strangeness and beauty of being alive at this particular point in history, capable of asking this particular question, then subscribe and like this video, because there are more questions like this one, deeper ones, and you deserve to be there when we ask them. The universe spent 13.8 billion years becoming something capable of understanding itself. Tonight, that something was you.